Good morning, everyone. Hope you enjoyed the conference up to now, and in particular the German HCI party yesterday evening. I see at least some of you recovered from it already. My name is Max, and I'm substituting our main author today, Martin Schmitz, who couldn't make it to CHI this year for professional and parental reasons. Before I dig into the very subject of the talk, let me give you a brief background of the more general research context that is executed in. Since a few years already, we are trying to support the fabrication of custom interactive objects that come off the printer with interaction capabilities. So in the design phase, you would not only design the 3D object's shape and structures, but also the interaction concepts you want to support on the object, like touch or touch gestures, like directional gestures on the surface of the object, tilt or deformation, and other interaction capabilities. And these capabilities are then realized during the fabrication process by basically combining both conductive and non-conductive material in a smart way, so that in the use phase of these interactive objects, there are basically two categories of usages that can be supported. The first category is such that you take the interactive object just as it comes off the printer and use it atop a capacitive touch material as you have it in a standard smartphone or tablet PC or a larger surface like an electronic wall or table. And there they can be used as parts of the tangible parts of the user interface or as building blocks to support a creative building process and so on. And the second category of use cases is to have these interactive 3D objects become basically the user interface of a smart object, an everyday appliance or whatever. So this is the background which we leverage for the project I'm going to present today, but in this case we were looking at designing a different kind of interactive 3D object that you can in the first instance consider to be a sensor of kinds. So the design is different because we have different use cases, and after the fabrication we have to distinguish two different variants of the usage that are intertwined. There is the offline use case where the sensors are deployed in the wild and applied during, for instance, a logistics process, and then there can also be used interactively on a capacitive display in the way I just explained a minute ago. To give you a better idea about what I'm talking about, let's look into just one sample use case, namely here a parcel delivery, and we have this mailman who is a little bit awkward or clumsy, and since he got already the final warning letter from his boss, he doesn't dare to take the blame for what he did, so he just delivers the parcels, and the customer in this case is left with the charter to prove that something abnormal happened to one of the parcels in the process, which is a pain in the neck, as we all know. So with our solution, the thing would look a little differently. On the sending side, someone would print a sensor and put it in the parcel, ship, the same thing would occur, but this time the recipient could just put the sensor on a capacitive display like an app on the smartphone, and then immediately see that one of the parcels was delivered properly and the other one underwent some abnormal event. Now, I think with this you now understand a little better what this pipeline means. So in the design we have to decide what kind of sensor do we want to build. Should it detect shock, which means acceleration or temperature or a load or whatever. And then in the fabrication process, of course, we have the choice to do it at home in a DIY process or as a service, for instance, in a makerspace or even a fabric. And then obviously, the one use case is this physical interaction with the process in the wild, so as long as the sensor is offline. And the use case now, I think, is also clear, either in between at different intervals or whatever, or after the process, the user can check whether a boundary condition, for instance, was violated during the process. Now, of course, this issue of monitoring goods has been around as long as ubiquitous computing has been around. It has been identified as a use case early on. So there's a traditional way of doing it based on electronics. And for the case of DIY, let's now quickly... My video has gone away. Let's consider... Okay, it's going to come. Anyway, so the customization that we have to do is concerning the value the sensor value types, but also the concrete parameters like the threshold value. All this has to go into the design and determines how the sensor is built. But using 3D printing, we also have an additional advantage, even in very tight packaging. For instance, we can adjust the size and shape of the sensor to constraints that we have in the process. Well, now let's look at the more traditional way of doing it using electronics. We might look at the DIY version of it, and then the traditional approach, of course, applies different kinds of electronics and assembly, and we have all gone through these tedious processes here that you have seen. So to become a little bit more serious, we know that for these processes, we have the cost of the electronics and of the assembly, and in particular, we have the electronics drawing power, so we have to supply some battery or whatever, and in total, although those sensors can be made quite cheap, they are not yet at a stage where you would have them used as one-shot sensors, especially also for the recycling of battery and electronics and so on. So you have to have a feedback loop, send back the sensors to maybe a service like Amazon, etc., which makes it not so useful, you know. And the customization, especially for the as a service case, is also restricted. So our solution is to use these, what we call offline sensors that recognize just a particular value to be considered without draining power throughout the measuring process. They are 3D printed in a single pass without assembly, and as you have seen, they can be read out on a capacitive touch screen. Now, you want to know how these things work, of course, but before I can explain that, let me quickly explain how the 3D printed objects provide their interactivity normally. What you see on the lower left is a cut through of you know, a touchscreen surface with the electronics below and the you know, rigid surface above. And if you now apply a 3D printed object, again, this is a cut through of maybe a cube or something, and you see in black the two conductive areas, then if you would apply on the kind of button you see on the left side, since there's no capacitive path in this case, it would not seriously alter the reading of the interactive area on the bottom. However, if you apply, for instance, a conductive medium like a liquid, an appropriate liquid, then you would see that a capacitive path is formed between those two interactive areas, and then pressing the button you can actually recognize a big difference in what you can read out on the capacitive side of the touch screen. Now let me mention that in this case it looks like you have to almost fill this chamber. In reality, quite often just a little bit of liquid on the inner surface of this material, of this object, would be sufficient to establish a conductive path. So you can sense quite subtle changes already. So this is the principle. And it is used and was used for us designing and building quite a series of different sensors and sensor value types. For the sake of time, let me just concentrate on two of them. First, looking at the tilt sensor, of a specific kind of tilt sensor, you have to custom design it for your purpose. In this case, we just want to detect even if it is just tilt by 90-degree once. So in this cut-through, we see two chambers, one with the liquid and the other one with the two conductive areas, as explained. That's the parts in red. Now, if you tilt this, obviously the liquid would flow from one chamber to the other. And as you put it back, the detected event remains persistent, and that's the important part of it, because you will only read it out after the process has happened. So this state change that is irreversible under the conditions in place, that's the important thing. So obviously, this kind of sensor, the way I drew it here, would not be appropriate for long-term exposure in the delivery that we saw in the little video. But for many purposes, this is also appropriate, and there are other designs. Let me move to, oh yeah, here we have a little showcasing of how the liquid actually flows, and this is a concrete example of this very sensor that I explained to you before. So now, for a pressure sensor, again, we'd have two chambers above one another, the liquid in the lower chamber, and apart from that, pretty much a similar design as in the last slide. But this time we would apply a flexible construction material that can be exposed to pressure and deforms then. And the deformation is pretty much what you do every morning when you squeeze a little toothpaste out of your toothpaste tube. So it would swap to the upper chamber, and due to the geometry, of course, would remain there even if the sensor goes back to the initial state. Now, I think with this additional explanation, you now understand pretty much the pipeline. We have a specific interactive tool for designing the different kinds of sensors, for defining the size and shape and the values to be recorded and so on. As for the printing, we are using a rather bottom-of-the-line two-nozzle 3D printer, so it's not that expensive. As to inserting the liquid, of course, printers could be built that do that automatically. Right now, they don't come off the shelf, so there's two possibilities. Either you stop the printing process for a moment, inject the liquid, and then continue the printing process so that the sensor can get sealed. For some of the sensor types, it's also appropriate to inject the liquid after the printing process using a needle, as is depicted in the lower part of the picture. But then you have to conceal the sensor by hand by some, adding an additional cover or heating it up a little bit. The deployment and sensing phase, as well as the interaction phase, I think are clear, and there's no need for additional explanations here. One more thing, a little few details about the implementation that we use. Our design tool is built in Java with OpenSCAD for the geometry part. I listed here the printer itself and the material we are using for both flexible and rigid structures, and the material we use for the conductive part. So this is pretty straightforward in the sense of enabling an average user to use these things. Now, as to evaluation, since the new and attractive part is the part with no user involvement, it's more appropriate to evaluate by conducting series of experiments in order to find out how accurate we can do the sensing, and this is what we actually did. Here you see in the same scheme as before an acceleration sensor, and obviously if you accelerate it, here in this case to the right, the liquid would swap over this wall, and one of the design parameters obviously is the wall height. And so we did a series of tests with different wall heights and 15 different acceleration values. And to give you a cue of the results, for instance, if you consider the transporting of the parcel in a truck, in a delivery truck, what you usually would want to accept is the usual speed up and slow down that happens in traffic, but you might not be willing to accept an emergency brake or even accident that would cause your parcel to be exposed to shock or to fast acceleration. And as you can deduct from the typical value for these two cases and the standard deviation, this can quite reliably be detected. So from the experiment results, of course, we are not really at the end of that whole research, but this gives hope that decent, useful sensors can actually be built. Second example for cooling, in this case, it's the low temperature threshold that is of interest. And in this case, you assemble a liquid that would freeze under a certain temperature, which is the threshold temperature, and that would break a wall and lead to the liquid flowing over to the other chamber once it's back in under normal condition and liquid again. And in this case, we tested, for instance, different wall thicknesses, and the result is that at 0.5 millimeter, which is a decent size for printing in a reliable fashion, we could reliably break the wall with this kind of sensor. So again, a quite promising result for these things to be actually useful. So with this I conclude, and I hope that I could show you that 3D printed offline sensing devices can be built, and there's room for more designs, for more sensor values, for more types of sensors. So I invite everyone to participate in this. So if you're interested, come see our website. And with this, I thank you for your attention, and I'm happy to take your questions.
So we have time for 2 questions.
Hi, Raf Raamakers, Salzburg University. So you mentioned a few times that it is do-it-yourself compatible, the technique, but I'm wondering why is it of particular importance that it's do-it-yourself? Because I can imagine in your scenario where Amazon is shipping 1,000 of these boxes with these sensors that they can just mass produce it similar to the products that are in the boxes.
Well, Amazon, for instance, has so many long-tail companies, that may just have a box office somewhere, and so for them to get access to a makerspace, or even sooner or later buy a 3D printer, this comes in handy, I think, because for many cases Amazon is just the mediator for a business, and this is just one example. Of course, there's personal-to-personal goods exchange. There's eBay, where people sell goods and so on, and this is a particular case where trust in the sender and the chain is important. So yeah, that's basically the background for that.
One last question.
Cool. Laura Olberg, University of Calgary. Cool work. I'm wondering, with some of the sensors, it seems like they would also be vulnerable to secondary issues. So for example, the accelerometer, if you rotate it or tilt it, it would also potentially trigger the same effect. So I'm sort of wondering if there's a way to isolate them, if it's worth trying to isolate these different types of sensing from each other.
Absolutely, and this is ongoing work. Yeah, for instance, this effect of the toothpaste, where you have more of a semi-permeable kind of structure. That's something that we're working on because it's not so easy. It's a little more delicate, but it can be done. That would, for instance, react to that. Same for the tilting, in the case shown here. If you tilt back the proper way or inverse it by 180 degrees, then everything flows back. For a certain time, as I said, there will be some liquid on the surface that will still be detectable, but it may dry out. And for these cases, you're absolutely right. This is the direction to go.